All right, now let's continue our discussion. Okay, so let me draw a fluid element again, and then it's subjected to a shear force, and then this bottom is fixed, and therefore what we have is this orientation. Right, now let me draw this final position. But of course, please understand that this is a rate, so it must be continuously deforming. Right, so now we have the shear stress, and we have this, in terms of the geometry, this value is, right, this is y, this is x. But since this is a differential volume, then therefore this must be dx, this will be dy. Now, since this is a rate, because it continuously deforms, then that means that we have dx all over dt, right? The change of position, the change of, let's say this one, the change of position per unit time, right? So now the shear strain can be based on this. Actually, it can be based on this angular deformation. But of course, we know that the trigonometric relationship is theta is just equal to this one. What is this? That's just the dx all over dt, which is just simply the velocity, right? V. Of course, that's going to be translated to the differential velocity, dv all over this one, this height. This will be dy, right? So therefore, the rate of shear strain is equal to some constant right here times the rate of shear, and also this is, you might ask, what happens to this tangent? Now, if we have a very small angle, then this is actually approximately equal to the angle itself. The tangent theta is just equal to this, tangent, what is this, gamma, tangent gamma is just equal to the gamma itself. That's the small angle approximation. Okay, because this is very small, then it's just the same. Therefore, we can write it here that the shear stress is directly proportional to the rate of shear strain, or this equation, right? So this is now the relationship for fluids, and this proportionality constant is called viscosity. Right? And viscosity is basically a measure of resistance, right? Resistance to flow. Right, so just like this one, if here you have the stress is proportional to strain by this constant elastic modulus, and in the same way we can have this shear stress is directly proportional to the rate of shear strain by this constant viscosity, this resistance to flow. So meaning that if you have a high or if you have a viscous fluid, very high viscosity, then it means that it requires you much force in order for it to flow. Okay, so the same way with this. So if you have a high elastic modulus, then it means that it requires higher force in order for it to deform. Okay, so again, you might also encounter this. Force is directly proportional to the deformation by this constant. Now, if it's just F and deformation, then this one is stiffness. But if it's force over area, force divided by area, which is stress, and the deformation divided by the original length, and that's going to be this one, and that's elastic modulus. Okay, so where can you find the data of this elastic modulus or viscosity for the different materials? You can find it in textbooks and other references. Okay, so now let's plot these equations. Okay, right? This one for solids and then for fluids. Now for solids, you already encountered this. The axial stress over the shear strain. And we have this for steel. Right? We have this yield point. Then we have this something like the maximum strength and then the fracture. Okay, so at first, at some level, from 0 to the yield, we have this elastic region, right? And the modulus of elasticity is actually the slope of this stress strain curve. Stress strain curve. Right, so that's for steel, for example, and then for other materials, probably something like this, or probably something like that, or for concrete, for example. Right, so we have different stress strain curves for different materials. Now for fluids, it's the same thing, because we have the shear stress, and this one is the rate of shear strain. Right, it's just the same as dV/dy, and we say that this one, if we have this equation, then that's actually a linear equation, right? So this is just a linear equation. Therefore, we'll have a linear graph. So the slope of the curve of the stress strain curve for a fluid, this is viscosity. Right? Okay, so different fluids will have different viscosities. So I mean, take for example oil, water, and air. Right? So for air, it's just easier to. I mean, it is easier to cause the air to flow as compared to the oil, right? So meaning we have a lower viscosity for air than with oil. So for oil, let's say we have something like this. Okay, so oil versus air. Okay, so now because of this, it gives rise to the concept of the types of fluids. Right? So for the types of fluids, we have number one, we have Newtonian fluids, or we can just write it in terms of this one. Okay, so for the types of fluids, we have Newtonian fluids, and here we have non-Newtonian fluids. Right, so what is this Newtonian fluids and what is this non-Newtonian fluids? Right, this equation right here, this is, if I remember it correctly, that's Newton's law of viscosity, right? So if your fluid obeys this Newton's law of viscosity, has a linear or a constant velocity all throughout, then that's referred to as Newtonian fluids. An example of these are oil, water, air, and probably many more. So we have this linear profile. But for non-Newtonian fluids, there are fluids that does not obey this or does not exhibit a constant viscosity all throughout. So there are this is further subdivided or classified into dilatants, the pseudoplastics, then Bingham plastics. Right, so dilatants, pseudoplastics, and Bingham plastics. Right, so for this, if you try to draw a graph, we have if this is our Newtonian fluids, the dilatants would have a graph something like this, right? So at first, it's easy to it's easy to flow, but then as it progresses, it's actually getting harder and harder to flow, right? So because you have an increasing viscosity right here. So at first it is easy, but then later on it gets harder and harder. Example of this dilatants are slurries and quicksands. Slurries and quicksands, right? So this is dilatants. Another class is the pseudoplastics. Now the pseudoplastics has a curve something like this. So at first it's very hard to flow, to cause the fluid to flow, but then as the process progresses, then it just gets easier, right? So example of this is paints. So at first it's very hard, and then some grease, right? Another example is the Bingham plastics. So the Bingham plastics is something like that's also something like a linear profile, except that it doesn't start from zero. It starts somewhere here, right? So example of this, the Bingham plastics toothpaste, right? So at first it doesn't flow. So if you apply a force that's below this threshold, then it will not flow. But then as you increase the force, right? So if you increase the force, then at some threshold, then you would cause this fluid to flow, right? Start to flow. So once it reaches this, then it will start to flow in a linear fashion, right? So that's non-Newtonian fluids. Okay, so the viscosity equation for this type of fluid would be the power law, or Oswald to Wiley power law, right? So it's written in our handouts that there's a shear stress equation for this as well. This one is linear for Newtonian fluids, and this one is non-linear. Okay, so there are still other types of fluids, like, for example, the viscoelastic fluids, right? Something like a gel, a food gel or something. Okay, so for now, let's just limit our discussions here. At least you are introduced to these non-Newtonian fluids, for processing, food processing, and chemical processing. Probably you would encounter this, the dilatants, the Bingham plastics, but in our discussions here, we'll just limit our topic to Newtonian fluids. Okay, so I guess that's all for the introduction to fluid mechanics. We have defined mechanics, and we have also defined fluids and differentiated from differentiated from solids. Okay, so there are still, of course, there are still differences between solids and fluids. You can also check their microscopic structure, and as well as the properties, for example. Right, so for example, for the density, let me write it in a new paper. If we have solids, liquids, and gas, right, so in terms of the properties, for example, the density, right? So for the density, example of steel it's around 7,800 kilogram per meter cube. And then this one, let's say water, that's around 1000 kilogram per meter cube. And then for the gas, that's just 1.2 kilogram per meter cube. So meaning we have this, the density of solids is very high as compared to this one, the fluids, right? Now you can also check the compressibility. This one is highly compressible, then this one is sometimes incompressible or assumed to be incompressible, and this one is also not compressible, right? Of course, typical, right? Because you might ask me, what about foams? So foams, of course, you can see that they can be compressed actually, right? So but usually for solids, they're not compressible, like for example steel bores or woods, concretes. But this one, they're incompressible or assumed to be incompressible. And also you can look at the molecular structures. Right, so I guess we have differentiated completely fluids from solids. Now let's move on to our lecture number 2, which is properties of fluids. Right, so properties of fluids. When we say properties, they're actually certain characteristics by which its physical condition may be described. Physical condition may be described, right? So first property is, let's say, the mass density, or just simply density. Sometimes when we say density, we refer to mass density, and the definition is mass per unit volume, right? So this mass per unit volume, if we express this in terms of equations, we have this rho is equal to mass per unit volume, and the units in SI, so this is density, this is mass, so that's kilogram, and this one is meter cube. And in English units, so this one would be pounds, and in terms of length, that should be feet cube. Okay, so typical values: water has a density of 1000 kilogram per meter cube, and of course, please take note at what temperature, right? At what temperature? So there must be a reference temperature, because later on we'll see that the density changes with temperature. Now for air, we have 1.2, that's 1.23. In our lecture handles, that's 1.28. That depends upon the reference, and the reference text plus the reference, this one, degrees, reference temperature. Okay, so again, at what temperature and at what pressure? What else? kPa, for example. At what temperature and at what pressure? Okay, so the question is, where can we find this density? It can be found in tables or textbooks. Right, so that's why when we say water, that's just we know that it's 1000 because it's already established and it's already measured. Okay, density is affected by temperature, and pressure. Okay, so for example, if we consider a container let's say we have at this temperature, at a certain temperature, we have, let's say, we have these gas molecules right here, right? So if it's cold, they are actually compressed. They are actually there's more number of gas molecules inside if it's colder. But if you heat it up, then these gas molecules will try to be in random motion, and sometimes they exits this window or this differential volume, right? So if it's a high temperature, then you have a lower amount of gas molecules here, so meaning that you have lower density. So that's just the point here, that the density is affected by temperature and pressure. Okay, another one is the specific weight. Specific weight, this is actually we can call it weight density. It's just the weight per unit volume. Therefore, our equation would be weight per unit volume, or since weight is equal to mass times the gravitational acceleration, then we can write it here. Then this mass per unit volume is just density, so we can also write as the mass density times the gravitational acceleration. Okay, so therefore for water, if we have 1000 for this, 1000 for the mass density, its weight density would be times 9.81. That would be 9,810 newtons per meter cube. Now for air, you'll also multiply that to 9.81 and you get the value. But again, you can find this in the tables, right? Okay, next property. The next property is the specific gravity. Specific gravity. Now, actually, this one is more, I think it's more precise, or more intuitive to say its relative density, right? Because it is a ratio of the density of a fluid to a standard reference fluid. Okay, so again, that's the ratio of the density of the fluid to a standard reference fluid. So in equation, we can write that as Sg is equal to rho of the fluid of your substance divided by the rho of your reference fluid. Now for the reference fluid, for liquids, our reference fluid is water, and for gases, our reference fluid is air, right? So therefore, the density of water must be used if your fluid substance is a liquid. Okay, so now by the way, this specific gravity, you can also find this in the tables, right? Tables, or we can also calculate it. If we have the data of other properties, then we can solve for these properties. Okay, so the next property would be viscosity. As I have said, viscosity is the fluid resistance to flow. And we have two types of viscosity. Okay, so two types. Okay, so one is called viscosity, just viscosity. I mean, it is referred to as just viscosity, or precisely, let's just write dynamic viscosity. Sometimes it's called absolute viscosity. right? And then this one we have kinematic viscosity. Okay, so if you recall in your subject in dynamics, and when we say kinematics, it all refers to just the geometry, right? The geometry of motion. Whereas this one, dynamic, or let's say kinetic, it's more on the of the involvement of forces or the mass. Okay, so for the dynamic viscosity, it's actually a shear force per unit area required to drag a layer of fluids. Okay, and the unit for this is kilogram meters per second, and this for the kinematic viscosity is just basically the ratio of the dynamic viscosity to the density. Okay, so our symbol for viscosity or dynamic viscosity is mu, and this one is nu. Right, that's the Greek letter, something like that. So nu, the kinematic viscosity, is basically the ratio of the dynamic viscosity divided by the density. And this one, if we have the unit of kilogram meters second, and this one is kilogram per meter cube, the unit would be meters squared per second, or other units such as Stokes, which is just equal to 1 meter squared per second. Okay, so you might question if this is a shear force, then how come there's no unit of force here? Okay, so I guess sometimes they use the this one, the unit of a kilogram, as a force, and you will encounter that in the subject of AB power engineering. They say a kilogram force, right? So at least here you will see that it's a meter squared per second, so it's entirely geometrical units, whereas this one, it's not. So it has a mass unit or a force units here. Okay, so where can you find the values of viscosity of various fluids? Again, you can find that in the tables. Okay, another thing to highlight here is that density is, viscosity is affected by temperature, right? Affected primarily by temperature. So if there's a table that says this is the viscosity, then you have to check at what reference temperature or at what reference pressure is that value for. Okay, and that's why we have correlations for the viscosity as a function of temperature. For liquids, we have A times 10 to the B times the temperature minus some constants. A, B, C are constants. And then for gases, we have these equations in our lecture handouts. 1 plus something like some terms right here, which I can't understand in my handwriting. Okay, so the point here is that there's an equation for this viscosity as a function of temperature, right? So these are correlations. When I say correlations, they are equations derived or obtained from research studies. Okay, so the next one is I guess I don't have much time, so we'll continue our discussion in the next video.